Now, visualizing motion along a straight line with constant acceleration basically means is we've done all of this stuff mathematically, but what does it look like graphically if we were to put it on a graph and actually see what we are talking about? So look at these three different carts, right? So cart 1 has acceleration equals to 0, which basically means that its velocity is not changing. And if you were to take their positions with respect to time will remain constant over a period of time. If you have a positive acceleration, that means your velocity will be increasing and your car will pick up speed as it goes. Similarly, if your acceleration is negative, which basically means is you're braking, what you will note is that it will cover less distance as you move forward in time. We have talked about this in terms of velocities before and what happens to their motion when we were talking about velocities, but this is another repetition of the same phenomenon, but now we are going to be using accelerations in order to define it. So what do the graphs of these velocities look like? So for the first one, when the acceleration was equals to 0, your x versus t graph, which is your position graph, is a straight line, doesn't move, doesn't change. Your velocity is constant, 1 meters per second, doesn't move, doesn't change. And your acceleration is completely 0, doesn't move, doesn't change. Now for the second cart, where there was a positive acceleration, that means the car was moving faster and faster as you were going. You will notice that the acceleration as you go up will cover more distance with respect to time. Your velocity will increase and your acceleration will be positive. For your last graph, where you were braking and your acceleration was decreasing, your position versus time graph will look something like this, where your velocity is decreasing and you're covering less distance as you go forward in time. Your velocity versus time graph will be negative, coming downwards, and your acceleration will be towards the negative side. So now let's look at an example. A trolley car in New Orleans starts from rest at the St. Charles Street stop and has a constant acceleration of 1.2 meters per second squared for 12.0 seconds. Draw a graph of velocity versus time. So in order to draw a graph, what do we know? We know our equation of motion, which is the first equation of motion, and we know V naught, because it starts from rest, is equals to 0. So at 1 second, final velocity is 1.2. At 2 seconds, the final velocity is 2.4, and at 3 seconds, the final velocity is at 3.8. If I was to draw a graph and extrapolate further, the graph would look something like this. Starting from 0 all the way to 12 seconds, as long as my acceleration remains constant, this is going to give me a graph between between velocity and time. So now the next question says, how far has a train traveled at the end of 12 seconds? The area between the curve and the time axis represents the distance traveled because it is a velocity versus time graph. So if we were to actually do the math, my delta x will be 1/2 base times height, because that's what the area under the curve for a triangle will be. So plugging in numbers, I get 86.4 meters. The last question is, what is the speed of the train at the end of 12 seconds? So an answer to this question could be read directly off of the graph, which means at the end of the 12 seconds, we have approximately about 14.4 meters per second.